Welcome to this presentation on optimizing word embeddings with search-based approaches by Federico Saro and Max Hort, which is me. I'm currently a PhD student at the team Solar at the research group CREST at UCL. In order to start this up, you'll have a look into a small background on word embeddings. In general, word embeddings can be used to represent words as vectors, which enables computation and comparison as used with normal numbers. On the right-hand side, you can see an example that shows three different vectors, king, man, and woman. And you can see that the colorful representations of vectors of man and woman are more similar than king and man and king and woman. This is due to the fact that man and woman occur in similar semantic contexts in various texts. The similarity of man to king is higher than woman to king, and you might make a comparison such as the similarity of king to man is the same as queen to woman. Such word embeddings are trained on large text corpora, and two popular methods to do this are Word2Vec and Glove. For both of those, there exist pre-trained models online that you can download and use for your applications. Applications that can be utilizing word embeddings are, for example, spam detection or recommender systems, but also software engineering tasks, such as for information retrieval, search for bug reports, and also code search. We are facing the following problem, which is that if you want to use word embedding or word embeddings or word embedding models, you might not have the computational resources to train them yourself. You might not have large enough text corpora to train them, or you don't have the time. Therefore, developers often resort to pre-trained models. However, they are trained on a different domain than the problem domain. In our case, we will be using the Word2Vec model trained on Google News articles, but if your application is not about news, then there's a slight mismatch of training data and problem domain. This follows the intuition that those pre-trained models could be optimized to fit the problem domain closer. In general, we will be following this given framework. On the left-hand side, you can see news articles that are used to train the pre-trained word embedding model. You can see the problem domain, which is different from the news article domain. And together with the pre-trained model, they can be used in an optimization setting to create an adjusted model. One approach from related work that can be mentioned is counterfeiting, that uses a list of antonyms and synonyms to adapt word vectors. Antonyms should have a high distance, synonyms should have a low distance or high similarity, and the vector space is preserved or is distorted as little as needed. The problem we are facing in our experiments is to make word embedding models more similar to human judgment. For this purpose, we're going to use a popular word embeddings evaluation method of word semantic similarity pairs that are judged by humans and used to evaluate the word embeddings. As you can see on the right, there's a list of word pairs that get a similarity score from 0 to 50 based on human judgment. For example, black and dark are very similar. They get a 47 out of 50. And bread and share, which you can see at the bottom of the list, only gets a 7. You compute the same similarities with the word embedding models and use this to show the correlation between word embedding judgment and human judgment. The dataset that is used for this is the MEN dataset or MEN dataset. There's a trained test split of 2000 and 1000 word pairs. Given this information, we are tackling the question of whether search-based approaches are able to optimize the semantic correctness of pre-trained word embeddings. In order to make this a searchable problem, we'll use the following representation. Solutions are represented by a solution vector, the vector S, that has the same size as one word vector. For example, in this case, it's a 300-dimensional vector which is multiplied by each word vector in the model to create an adapted vector called W prime. The solution vector is initialized with a vector of ones and a little bit of noise. We have two mutation operators that either add noise to a single element in S or add a noise vector to S. The results we got from applying local and global search methods can be seen in the following chart. The base correlation that is achieved with the pre-trained model is indicated by the dotted line around 0.77. We use a random search method that performs quite similar, always around the 0.77, and we use hill climbing, taboo search as an extension to hill climbing, and GAs to optimize the semantic correctness. As you can see, all those three methods are able to optimize the base performance. However, they perform similar. So there's no statistical significance among the three solutions. They are all able to outperform the base performance. And this concludes our presentation.